Welcome, everybody. Today we are happy to have on our SFSN seminar John Schwenck, who is our alum. Let me say a few words about John. He has been a quantitative analyst at Wells Fargo at their Consumer Artificial Intelligence and Machine Learning Model Development Center for the past 3 years. Being in a centralized group, he has had the opportunity to work on projects ranging from marketing, offer optimization, branch localization, local modeling, customer lifetime value, net present value forecasting, and currently an internal NLP-based sentiment analyzer. He received his Master's of Science in Statistics in 2021 from Statistics Department, Texas A&M, under Dr. Irina Gainanova, where he focused his research efforts on biostatistics applications in the realm of wearables, tracking, and diabetes, hypertension management. He is the creator of the R package BP, which has collaborative effort with Johns Hopkins University to develop a suite of tools for analyzing blood pressure data. Prior to his graduate studies at Texas A&M, he worked for a natural gas distribution company, SJI, and helped develop the company's first data science department, whose work spanned the wholesale community, trading space, and pipeline infrastructure development. He received his undergraduate education from Penn State University in 2016 with degrees in economics, Bachelor of Science, and supply chain information systems, also Bachelor of Science. John will present today a talk, Artificial Intelligence and Machine Learning Model Development from Academia to Industry. John, welcome.
Thank you, Dr. Vidakovic. Really appreciate the intro. Like you mentioned, we're going to talk about end-to-end model development, but extending past the idea that we typically use in industry where we're talking about, okay, we have some data and we want to build a model and productionalize it. I want to go even before that into your guys' realm in academia and talk about the full life cycle of a algorithm or a method or a paper or whatever you want to call it. So you did all the introduction for me, so I don't have to spend too much time on this slide. But yeah, like you mentioned, Penn State 2016, A&M alum, Giga Maggies. We did the blood pressure research, and yeah, this is just a little bit about the background as you already touched on. So let's get into what is the full life cycle from the moment you guys have an idea to the moment that our team implements that idea into production. So just kind of going down the list here, this is a rough timeline, I guess you could say, of how that idea permeates and through all the trials and tribulations to get to the end result. So what's typically the finish line for you guys, which would be a paper or a conference proceeding or something like that, that's usually the starting point for us, right? We're going out, we're looking at different papers, we're trying to do a bunch of, I guess you could call it applied research, where we're taking in the info that you guys come up with and finding ways to apply that. So just going down the list here, when you guys come up with an idea, it's either extending some sort of existing method, or there's like a knowledge gap in a certain research area that's been unexplored, future directions of like previous work that you did. And so once you have this idea, what do you do with it? Well, you want to prove its mathematical feasibility, right? So you run the proofs, you do all that. Then you would want to apply it on simulated data to see how it performs asymptotically, any kind of like extremes to that theory, just to really stress test it. Then you would have the real world example. A lot of times in papers, they have a real world example. And we'll touch on this a little bit later, but then you want to pass it through peer review, where it's have someone kind of double check your work for accuracy, point out flaws, and then ultimately you publish it. This is all very familiar to all you, so I won't dwell on that. But that's the point where from our standpoint, we have some sort of applied problem. A line of business comes to us and says, we have, $1 million in our marketing budget. We want to find out how to best use that money to reach the most amount of people and to retain the most customers, as an example. So then we would take that problem, we develop a very high level framework, and we try to look into the academic sphere to see, okay, what kind of papers would be relevant here? Like, given our framework of how we think we can solve this problem, what methods are out there that we could leverage? Then the hard part is we have to take those papers and translate them, right? So a lot of papers are written with either pseudocode or some sort of just generic mathematical algorithm that's kind of high levels, kind of vague. And so we have to take that and translate that into either Python code or R code or C++ or whatever. And then we got to experiment with it. And we want to test on different, multiple methods on oftentimes. And we want to see, okay, what's like the best solution for this problem? And then once we have that solution, then we have to run it through some compliance checks for regulatory risk and financial risk and so forth. And then finally we deploy it. But once we deploy that method, we still have to monitor it, right? Because it's unseen data and we don't have, if it's a supervised problem, we don't have the labels like coming in. So we have to find a way to monitor the model's scores, the model's performance. So that's like kind of end to end, the whole life cycle here. But then what I call the chicken and the egg problem is this constant battle of like, who's motivated by who? So these are some questions for you guys to ponder. Let's start with the academic lens first. So where do ideas for future work come from? We kind of touched on that already. How do you prove a method's usefulness? So sometimes papers are super abstract, super theoretical, and in isolation, they might not seem practical, but they serve to lay a foundation, right? And oftentimes these abstract or theoretical papers they end up being useful down the road because at this current juncture, at this point in time, it might not serve a specific use case, but it might down the road. And we see that a lot with like computer science. A lot of these like computer science papers that come out, they don't seem super valuable at first glance, but then, 10 years later, you come back and like, oh, that could be really useful. You see this a lot with Bayesian statistics, right? Back in the 90s, it wasn't that relevant because we didn't have the computational power. But now, fast forward to today, we have super processors that can handle all of that computation without batting an eye. There was a question that one of my professors always gave that it's stuck with me. It's, when you're doing research, is it better to derive a method and show that it solves a given problem? Or is it better to take a given problem and derive a method to solve it? There's not really a right answer per se, but it is an interesting way of framing how you approach the research. And then from the industry standpoint, are the most complex methods necessarily the best solutions? There's a lot of research with neural networks and all these very complicated methods and papers, but are they necessarily the best? Well, that also kind of depends on the use case. It depends what you're trying to solve. And we'll get into all this later. Is one solution enough, or should you consider a multitude of different solutions? And what I mean by this is not for the same problem, but sometimes the business problem has multiple components to it that you want to factor in. If we're looking at, is a customer growing their balance? Well, are they growing the balance itself? Are they using the account a lot? Are they trying to game the system where they just deposit a bunch of money, take the money out, and take the offer, right? These would be three separate components that we would try to model in tandem. So I guess I can throw this question out there that you guys can think about. What would be the limitations of real world examples in academic papers? So when you read a research paper and it has a real world example, could anyone give me an example of like why that would have some serious limitations from an applied standpoint? I have like a 5-second rule. If no one raises their hand, I'll just answer the question. But okay, well, the one thing is there's a lot of assumptions that have to be made in academic papers that don't necessarily translate, right? So like in real world data, or rather in these real world examples in papers, the data is often super clean. They don't account for missing data. There's different real data, like actual industry data has different data types or structures or crazy outliers. A big problem that we have at Wells Fargo is the different time scales. So you might have one variable that's on the monthly level, another variable that's on the daily or hourly. So how do you kind of find the common denominator to build out the model in an effective form that captures all these different complexities? And on the other side of the coin, what are the limitations of applied problems when conducting research? Again, give it 5 seconds. Anyone have a thought? So in this context, there's often too many factors to consider, right? Applied problems are so broad, so vast that in a research setting, you have to hold something constant. And when you hold something constant, that usually comes with a whole set of assumptions that you have to make, which are necessary, right? Because you're trying to prove out one particular method or one particular framework. And just nature of how you do that research, you have to layer in all these assumptions. So it's kind of a balancing act of like, okay, how do we account for all these assumptions that don't necessarily apply in industry? And then from the other side of the coin, how do we build solutions that are all encompassing enough to solve a breadth of different industry problems? So when I say chicken and the egg, it's does industry motivate research or does research motivate industry? And there's not really a right answer to that, but something to think about. So if we think about the actual challenges in industry, we kind of just talked about some of them, but prediction versus inference, uh, these are depending on the use case. In a say you're taking fraud detection, right? I don't care at all about the uncertainty quantification. I purely just want the highest accuracy possible. So in this case, you take those super complex black box neural network models, that's fine because we want to we want to stop the fraud in its tracks before it happens. But other situations you might consider, okay, how does a particular group of customer, if we're doing personalization and we want to like send certain products or certain services to different groups of customers, we want to infer things about that population. Or if we're going to approve or deny someone for a loan, we want to be able to be very certain that the predictions we're making make sense. So in that case, it's kind of the opposite. We do care a lot about quantifying that uncertainty. Scale is another really big problem. Particularly at Wells Fargo and tech companies and everything else, there are tons and tons and tons of data. So are we talking about millions of rows, billions of rows? We have credit card, every transaction data point on every single customer. And we have 55 million plus customers. So we have 55 million customers, and each of those customers are making thousands and thousands of transactions. So we have trillions of rows of data. So a lot of these traditional methods, they might not apply. And there's a lot of things you have to account for as you scale up that data. Leader versus laggard. What I mean by this is really what stage in the business cycle are you? If you're like a cutting edge tech company or a company that's trying to really leverage these like super novel machine learning or AI methods and models, you're going to be willing to take that risk to have that first mover advantage, right? So you're going to be really trying out the latest and greatest stuff out there. But if you're a laggard, and that's not necessarily a bad thing, it just means you have kind of an established business model and you don't necessarily care about having the most cutting edge stuff, but you still want a robust framework to solve the business case at hand. So I guess I could say Wells Fargo is a bit of a laggard, not in a pejorative, but as we have an established framework where we offer services and financial products to our customers, and we don't necessarily need the most complicated methods to solve our problems. There's also risks. This is oftentimes overlooked in a lot of research for obvious reasons. It's not super pertinent to proving an algorithm, but from an applied standpoint, like we always have to consider regulatory compliance, financial risk, reputational risk. The difference between us and Google, right? If you get a Google search wrong, well, you just search again. That's a pretty minimal error. But if we approve or deny someone for a loan that was otherwise pretty trustworthy, that's a $10 million lawsuit, right? So you have to really consider those kinds of risks when you're formulating your business problem. Interpretability is a big one for a lot of the reasons I just mentioned. And then also multiple data sources and data types. So especially now with large language models and multimodal models and every other thing, a lot of these models have to deal with tabular data, images, audio, natural language, video, etc. So those are just things to consider. So if we get into the actual model development, the first step is the data source, right? So where are we getting the data? Is it internal or are we getting data from third parties? So there's kind of two camps here. I think, and I want to preface this by saying any company is going to have their own data in some form or fashion. Every single company has data. How they use that data is a different story. So when I say proprietary, I'm talking about companies that specifically collect proprietary information about their customers that they can then group up and use that as a service to other companies. So the most obvious example is Facebook, right? They're not selling your data, but what they do is, say you're a construction company, you're a mom and pop, coffee store, whatever. You have some data on your customers. You want to market, you come up with an ad and you want to market that ad to a particular group of people. You can send Facebook information about your customers. They then leverage that information with their own proprietary information, and they come up with ads based on the business's needs. So then they have that as a service that they can then offer advertising or marketing or whatever it is. So the internal data is like super valuable, right? There was an analogy someone told me once that's always stuck in my mind. And I think it's genius. If you think back to the gold rush of 1849, there were a lot of people that lost and went bankrupt and didn't find gold. There were a couple of people who made it, who struck gold and were, rich beyond their wildest beliefs. But that was a huge discrepancy between the amount of people who lost out and the select few people who actually found gold. The people who indisputably, as a whole, made the most money were the people selling the picks and the shovels. So the people who were selling the picks and the shovels didn't care about whether the gold miner found gold or not, because the gold miners who made it and the gold miners who didn't, all of them bought the picks and the shovels. So that's kind of the analogy to like how a lot of these, mostly tech, but not necessarily just tech, a lot of these companies, they harness this data and they can use that data as a service to any kind of business. So a Facebook can sell, or they can sell their data service to any company, the mom and pop barista to the construction company to Wells Fargo to anyone, any company that needs advertising through their platform, they have that internal data. So they're kind of impartial to how the boom and bust cycle of this AI and machine learning cycle goes. On the other side of the coin, you have third-party data. So this is data that comes from vendors who aggregate their data across individuals on a wide spectrum of sources, public or private. So and again, they don't sell the actual information, they sell some service. So they'll send model scores or probabilities about customers, or they'll send information about what they're interested in or things like that, but they're not selling the actual personal, they call it PII, personally identifiable information. So the advantage of third-party data vendors is that they do all the work for you. So you pay them, they send you whatever, variables you need, and then you can add that into your data set. Now, the problem is they try to collect so much data about so many different variables and characteristics about customers that not every customer has a data point for every single variable. So you often get these like very sparse data sets, and a lot of them are not processed correctly or cleaned correctly. So you still have to do a lot of that on the back end, but it does speed up the process of actually obtaining the data. So examples of this would be like Experian. That's probably the most common one, right? It has a whole bunch of like credit related information. And so that can be sold as a service. So where does Wells Fargo sit? We're kind of in the middle. We use third-party data, but we also have our own data, as I was saying before, about like credit card transactions or debit transactions or investment transactions, right? We have all of this proprietary data that we can use, but we also take in third-party data when we're doing like marketing or advertising, or even if we're doing like call center models, right? And we want to know information about like, okay, where are the calls coming from? What are like the calls like? What is the topics that they tend to talk about that are the pain points and the bottlenecks? So we kind of have a healthy mix of both, in my opinion. Now, in terms of the modeling itself, this really varies pretty widely across companies. So you have some that are purely in-house analytics, pure in-house model development. Wells Fargo being actually, we're not exclusively proprietary, but my group is proprietary. We have our own Python package that we developed that does all of the modeling from end to end. This really allows for a lot of flexibility in doing the research, doing what we were talking about before. We're going out and reading papers, and I have a couple of use cases at the end where I highlight this, but it's a lot easier to incorporate that into a Python package that we developed rather than having to negotiate and barter and, you know, the months and months of back and forth with all these third-party vendors to try to incorporate a model such as that, right? And there's obviously a lot of IP related issues with that as well. So while it is more flexible, it's a lot slower to implement just because you have to do all that coding yourself. Um, and yeah, and so then in terms of the third party stuff, third party modeling vendors, they have out of the box solutions that, you know, you just give them the data, upload the data into the modeling framework, and then they run all the models. They do all of the model development, which I'll get to on the next slide. All of that's done within the vendor itself. Um, the really big advantage of using them is you don't have to worry about like distributed frameworks. Again, when you have millions or billions or trillions of rows of data, that can be a huge headache to try to account for that, because if you read a research paper, you first have to translate that into a Python code, right? And then you have to translate that Python code into a distributed framework, whether it's PySpark or Apache Spark or whatever. So the vendor doing that for you saves you a lot of time in that sense. But the drawback is there's limited flexibility, and a lot of times they kind of have a set number of algorithms that they let you use, and that's it. Examples of this would be like a data robot or an H2O or an Alteryx and so forth. So the modeling pipeline at Wells Fargo works essentially like this. It's a 13-step process. I like to think of it as. First, you formulate the problem. You work with the line of business. You see, okay, what exactly are you trying to solve? Then once you agree, there's usually a statement of work where you give it to them and they say, okay, this is what we're hearing you say your problem is. This is the solution we're proposing. Do you agree? Do you disagree? Do you have any questions? Once they give us the okay, we have to ingest the data. And again, that could go back to what we just talked about, whether it's vendor data or whether that's our own data or a combination of both. We have to do all of that data aggregation together. Then we have to build a response variable, which you think would be super easy, but it's actually one of the most labor intensive parts of the entire model process, because if we have a particular problem that doesn't have an associated variable, we have to create that variable. So if it's like what percentage of people left the company, right? We want to build a retention model. What percent of the customers who opened an account withdrew their account? That we don't have that as a variable, so we have to create that. Then we have to merge in all of the predictor variables. So we have what's called a feature store. This is kind of like a repository of all the variables for all the customers, and we just pull that in. Then we do the very typical train, test, holdout, data split, and then we'll want to reduce the feature set from like a preliminary model. So we have, I think like 3,000 variables. So we want to collapse that down as much as possible. So we'll run like a preliminary model just to see what's relevant or not. And then we'll do some, exploratory analysis, correlation analysis, dimension reduction techniques. All of that kind of is in this 7th step here. Then we'll go and actually implement the algorithm. So whether that's something from research or whether that's something from a vendor or just kind of like a basic GLM, we run all these different combinations of algorithms on the final data set, the reduced feature set. And we assess its performance with what we call a leaderboard. So you'll have like if you run 100 different algorithms, you'll see how do all those 100 stack up against one another based on some performance metric. So if it's a classification problem, how do the AUCs compare for the training set versus the test set versus the holdout set, and so forth. Then you want to evaluate the final model on the unseen, the holdout data, run some model diagnostics. And then once you come up with like that final model, then it's all like the annoying stuff. Then you have to send it through compliance. You have to run it through the regulators. You have to make sure that like you get approval and that it actually is compliant with all of we just have to dot our I's and cross our T's. And then we have to send it to model validators, which is a totally separate team that they rerun everything because reproducibility is very important. So they rerun all of our tests. They make sure, tie the seed together, make sure that you're starting from the same point, you're getting roughly the same results, all that kind of stuff. And then they evaluate like the financial impacts. Like, okay, if this goes wrong, how much of a cost is this going to be to the business? So all of that stuff has to get done. Then once you pass all those tests and all those approvals, then you deploy it into a production environment. So this is where you have new data coming in, and you have to assess how does this model that is trained on this particular set of data for this particular time frame, how does this model perform out in the wild, so to speak? So how does it perform on truly unseen data going forward, right? If we build our model from January to May 1st of 2024, when the June data comes in, we're going to apply that model on the June data and see how it performs. And then if it's totally out of whack, like if the model scores are completely different than what we had from the model that we trained on, we have to kind of go back to the drawing board, start all over, run the whole process all over again. If not, then you're good to go. Then that translates into the ads you see on social media or the TV advertisements or the fact that, you go to the ATM and there's always cash in the machine, where before, you go to an ATM and there was nothing there. Or you go to the call center, it's more efficient. All of these like business improvements stem, at least in the group that I work in, they all stem from these kinds of models. So that is when, once it's deployed, then the lines of business can actually use that and make business decisions to try to optimize their group's activity or problem or whatever it is, right? So just as a visual, this is kind of what that process looks like. So we have what's called a metadata file, which is just a whole bunch of information on the predictor variables themselves. Are they categorical, continuous? How many missing values are there? Where it's the data sources? Because a lot of times we're mixing in data sources together, right? When I was mentioning vendor and proprietary data, those are different data sources. So we have to join them all together. And the metadata file has all of the paths that create that link. And so then we'll have the process data and then the target variable, combine that together, what's called a master data set. This is all our lingo. I don't know. I'm sure other companies have different names for it. But then we go through the train, test, holdout, and everything we were just talking about. This is just kind of a visual guide to explain how that works. So qualitative considerations. There's two types of model bias. There's one from like the mathematical definition of it. Does that because if there's mathematical bias, then that could lead to diminished performance going forward in like a production environment, and that could lead to financial costs. But there's also like the social implications, the social definition of bias, right? So is there any overt or covert kind of discrimination or like are we favoring one group over another? Like all of that kind of stuff has to be accounted for. And these are all things that should be highlighted or pointed out or fixed as we go through that compliance and that model validation step on the previous slide on step 10. And yeah, like I said, the legal ramifications. So if there is social bias, that's very likely to lead to a lawsuit, right? There's financial risk if we get the predictions wrong, and let's say it's some sort of capital markets model, like a trading model or whatever, then There's risk there because we got the predictions wrong. We made a bet and we lost. There's also reputational risk. So maybe there's no lawsuit. Maybe we didn't lose a lot of money, but a lot of the perception of the business is diminished, right? Because of one thing or another. So those are all risks you have to consider. There's also like upstream, downstream risk. So if you have a model that feeds into another model, and that model feeds into another model, and your model's out of whack when you're monitoring it, that's going to throw off, sorry for the light, that's going to throw off all the rest of the models downstream from that. So you have to always consider the effects upstream and downstream. Again, my little 5-second question. Can anyone think of any other qualitative considerations that might go into model development? So the one problem that we often face is the lines of business. They're not tech, like, I mean, some of them are, obviously, I'm making a generalization, but more likely than not, they have their own domain expertise and they're not technical. So being able to relay non-technical information back to my group in a technical way and then relaying technical information back in a non-technical way to them is often a big challenge. And that's something that you really want to get right, because the first step in the process is making sure you identify the problem correctly and you're solving the problem correctly. So if there's a disconnect, there's a miscommunication between what they want and what we're offering, the whole thing is useless, right? So we have to go back and make sure there's that constant communication. Um, and then I touched on this before, but interpretability is obviously a very, very big factor. There is a legal requirement for us. If we deny someone for let's say a mortgage, we by law have to provide them with, it's called a oh man, my manager would be so upset with me. I can't remember the name. An adverse action uh notice, I think it's called. And so we have to explain to them why we denied them and what reasons we denied them. So take this full circle, go all the way back to the complexity of the algorithms. If we're using some super complicated neural network model to predict if they're going to be approved for a mortgage or not, that's going to be very difficult to explain to them, because even from a mathematical framework, that's hard to explain, right? So oftentimes we tend to stick with more of like the lighter weight stuff. GLM, you'd be surprised, it's super basic, but oftentimes that's like a very good candidate for models because they're very easy to explain. Ensemble methods are the same way, because the nature of how the trees and the nodes are distributed, there's like a very obvious, like, okay, there's this probability with this factor, right? And so there's a lot of visuals you can provide to the customer, right? Like a partial dependence plot to show how does the effect of the variable change as you move along the range of that variable. So like income level, let's say income level was an explanatory variable, and likelihood to open an account was your response. The higher the higher the income level, let's say, then the higher the likelihood of opening up an investment account or something like that. Now, just FYI, we're not allowed to use income level in many times because it's a proxy for some of these bias variables. But just to give you a simple example, that would be one thing. So let's go into the case studies. I have two here. The first, the problem we were given was we have data on all of our current branches across the US. Deposit info, demographic info, all sorts of different financial metrics. And we want to predict new locations to open branches. So we don't have any of the branch specific information by definition, because we're trying to open a location. We're trying to find places to open a location. But we do have the demographic data. We have all of the regional data. So does anyone have an idea of how you might approach that problem, or what kind of method or general framework you would use? So what we did was we initially started with a spatial varying coefficient model, and I'm going to switch to this paper here just so, because I know this is recorded. So if anyone wants to go back and reference what the paper is, here it is. Dan Bond et al. 2021. The whole idea here was, okay, it's one thing, a linear framework, or I guess like a GLM framework, wouldn't apply because the parameters, or rather the coefficients, are going to be fixed, right? But we know there's spatial dependencies near things are more similar to things that are farther away. So we tried to develop a framework that would account for the changing coefficients as you change the location on the map, right? And we have branches all across the US. So we kind of considered all of the US as our population of interest, of our region of interest. So that wasn't necessarily a problem. But the issue was that it mainly works for, like, if you had data on specific locations and you wanted to predict future data on those specific locations, it would work, but we want new locations. So we ended up switching gears to a linear mixed effects model. Again, just the classic version of it, nothing groundbreaking. But in this instance, we had different hierarchies, right? So we had east, west, north, south, central as like our 5 huge regions. And then within each of those regions, we broke it down by state. Within state, we broke it down by county. And so we tried to find like the within subject effects and between subject effects, or the subjects were the branches. And then using that, we could extrapolate a little bit better to these regions, because we would be tying the regions to the predictions rather than like a specific unseen point. So that's something that we're currently working on. Yeah, so that's the first example. Again, qualitative factors. This is just like with banking, there's a big regulatory issue with like redlining. So you want to make sure that like you're not favoring super wealthy areas and discriminating against lower income levels, lower income regions, right? So you want to make sure that you factor that into the model as you go about. So that's also something we have to consider. So the second example I have is direct mail marketing. So I want to ask you a question. You don't have to answer, but when was the last time you responded to a physical advertisement in your mailbox? I know for me personally, every time I get an ad, I throw it directly in the garbage. So what are some of the statistical considerations of that? Well, if we're sending out mail to 10 million people, our response rate is going to be microscopic, like 0.0001%. Or maybe 1,000 people respond, maybe 2,000, tiny number. So that's going to totally throw off the framework of how we build that model. So this Pizzolo paper, and again, I'll just kind of highlight it here. This is a 2015 paper, and what we used here was he had a way of it's called undersampling or downsampling, as we call it, where you try to reduce the majority class to bring it to a point where you hold the minority class. So all the people who responded, say 1,000 people responded, you would shrink all of the people who didn't respond down until that proportion is, say, like 80% non-responders, 20% responders, instead of 99.999% non-responders and 0.0001% responders. You shift that distribution down so that it's a more manageable distribution for your modeling frameworks. And again, this applies to other channels as well, email, banner, social media, whatever. But direct mail specifically is like really difficult to model just because of that very problem. Like most people are going to throw their mail in the trash whenever they get an advertisement. There's also data considerations for customers, like existing customers versus prospects. If we have an existing customer base that we want to market a new product, like let's say we have a Premier account where if you have an existing account, you're eligible to upgrade your account. Well, we only care about existing customers. We don't care about prospects. So what we're going to do is we're going to specifically condition on those existing customers, and that has a whole separate data set than the prospects, right? Because the customers, we have all their transaction history, we have all their account information, we have all this extra information that we can leverage. Prospects, on the other hand, we don't know anything about them other than demographic information or zip aggregate information, like regional information. So it's a totally different framework of how we model products to existing customers versus how we model products to prospects. If we want to entice people to open, I guess I'm not supposed to say entice. If we want to attract people to open a new account and we consider customers and prospects, we have to account for the fact that we have different data sources and different data points for every customer, right? So that's another challenge that we have to work through. And then also by nature of sending physical mail, there's like a very serious time component where it takes a month for us to send all the mail out. And then and then we give them like a 3-month window for them to respond. And if they have to go into a branch, that's another time component. So that really affects the response window. So when we are pulling in all the predictor variables, we need to account for that at the time of them receiving the offer, even though the response might be some point in time. So if we're doing like a net response model, so of the people we sent mail to, how many of them opened up an account? So that, let's say that's like a 6-month lag. So they get the mail, or we send out the mail, they get the mail 1 month later, they open their account 2 months later, and then we have 3 months of data to see did they open up their account or not. And then of the people who opened up their account, how many still had their account open, say 12 or 2 years later, or sorry, 12 months or 2 years later, right? So now it's kind of like a conditional probability, but there is a huge time discrepancy there that we have to account for. So yeah, that's just an example of 2 case studies there. Now in terms of like future state cross collaboration, I like to call it, these are just 3 bullet points for faculty and students that I kind of came up with on my own. Just things that I thought might add value for both the faculty of the student as well as the company. So from a faculty perspective, anyone, when we partner with researchers, we can, and faculty, we can kind of bridge that gap that we've been talking about this whole time. Like, what is the discrepancy between the algorithms that you come up with in a research setting, and then how, and the actual deployment of that, kind of that chicken and the egg problem. I think working together on papers and working together on different research directions, that could help bridge that gap a little bit. But also like information exchanges, right? If you have a new method that you would be willing to share with us, we could then provide you with data that you could use to prove out your use case when you're writing your paper, or even presentation exchanges, right? So colloquium, if we get to see some colloquium invites, then we could come on as guest speakers as well. And vice versa. We could bring you in. Now, that's just like things I thought about. I don't know if that's like Wells Fargo approved or not, but that's just, I want to preface that by saying that. But in terms of any students out there, coding data competitions, I know Texas A&M has a really awesome datathon, which I was a part of. That was a really cool experience. Really gets you thinking about like, how can we apply the stuff that we're learning in class? How can we actually apply that out in the wild? And my 2 biggest bits of advice that I think serve everyone in the STEM field, and particularly in the statistics department well, is become exceptional programmers. So you don't have to learn every language, but pick one and be an absolute wizard at it. That will serve you very, very well. And if you know that like the back of your hand, then you'll be able to translate papers. You'll be able to do all the research components a lot better, because you can then think about it. Okay, how does this actually work from a computational standpoint? What is the time complexity of this algorithm? What is the space complexity of this algorithm? When it scales, we have to consider all these things, right? And then lastly, just be insatiably curious. I think the more curious you are about the world around you, the more it's going to motivate different directions that you can take on your research. So that's kind of going back to the question of like, does research motivate industry, or does industry motivate research? There's not really a clear answer on that, but I think the more in tune you are with what's going on around you, and the more curious you are, the better you'll be able to come up with research that actually serves industry well and serves even other researchers, right? Because it's going to cast a wider net. It's going to be able to encompass more use cases and lessen the amount of assumptions and all that kind of stuff. So that's really all I had. Any questions?
John, thank you very much. This is really amazing talk. You really sort of brought to academic part what is important, and in the industry and in practice. when we do modeling, we think only about model itself, but there are so many other issues, financial, social, and other that come to the play. And thank you for very nice talk.
Of course. Thank you all.
I'm opening now this discussion. Please, if you have question for John, just go ahead.
Could you give me an example where a modeling effort was abandoned since you could not find a satisfactory solution? Yeah, so that's that actually was what happened with that spatial model. Going back here, we realized that the SVCM model just didn't work. From a theoretical standpoint, we didn't think that one all the way through, unfortunately, but it wasn't able to work on unseen locations. We thought maybe we could use some of like the regional estimates and kind of extrapolate out a little bit, but it just performance wise, it didn't work. So we had to think of other solutions, and that's where we came up with like the hierarchical model. Because the hierarchies we can map to any given location and any given branch that exists. And so that was kind of how we approached that. There's a lot of experimentation in our group. So there's a lot of times things just don't work right. There was another instance where I was building out we call it a customer lifetime value, which is just a fancy way of saying net present value for our customers. And we tried using a bunch of different semi-parametric methods for the retention rates. So it was essentially a survival model to see how long a customer would last. And given how long they would last, we would then discount that back to today's dollars. So if a customer opens up their account in May 1st, 2024, we would look at, I think it was 10 years. And let's say that customer A is with us for 8 years, customer B is with us for 10, customer C is with us for 15 years. Obviously, this is retroactive, right? So if they opened in 2000 or whatever, but then we would look and see, okay, like of that 10-year cutoff, how many are still with us? And then of those who closed early, what was the retention rate? And then we have to wrap that into the net present value. That just didn't work. The performance just wasn't as good as the model the existing method that they were using. And sometimes the data just is what it is, and it just it's not a bad method. There's nothing like theoretically or fundamentally wrong with it. It just didn't work on the data. So we kind of gave up on that one. And so as an alternative, what we did was they were doing everything in Excel. So we just completely automated the entire process for them, which was also a really cool experience to see how the code that they did have for the model that they were working on, the existing method, we got to see how to translate that into a Pythonic, like a programmatic solution, which is pretty cool.
Any other question? Please chime in.
Someone's typing.
Yes.
Thanks for the interaction, Joe. I appreciate it. And also, while you're thinking of your question, if anyone ever wants to reach out on LinkedIn or has a question, feel free to email me. Dr. Vidakovic, I can send you my LinkedIn and an email, and you can forward it over if you want.
Thank you, John.
Actually,
I wish that your talk could be presented to our master students to see what they, for example, expect in the industry and what are the intricacies of their statistical work in the real life.
Yeah, definitely.
Yes.
Hey, I'm always looking to make a trip back to College Station.
That's terrific.
Okay, so on fraud modeling, how do you find sufficient number of responders to learn from given that there are relatively few examples that you okay Yeah, so that's a great example. So that is actually the motivating. That's a great question. So if you read this paper, the original Pozzolo paper, the use case that motivated this whole method was that exact problem. So it in fraud detection, fraudulent transactions are normally outnumbered by genuine ones. This is like the exact problem that you're talking about. And so this would be the solution to that problem. You would take all of the fraudulent instances that we have. And again, we have data, we have so much data going back like 20, 30 years. So this might be a totally different approach for, say, like a startup company who doesn't have that much data. But from the Wells Fargo lens, we have so much data that we do, even if it's a very small percentage relative to the majority class, we can use this Pozzolo method, this undersampling method, to try to bring the distributions down to a more manageable level so that we can use kind of like these tried and true methods. So I encourage you to read that paper. You'll find all the technical details there. But that was something that we had to translate and then apply into our model. And that's also one component of the modeling, right? So that's only when we're dealing with like the processing and the preliminary, like the data splitting, all of that is all preliminary to the actual modeling algorithm. So that's a totally separate process we had to do for that particular piece, right? So that's a great question. I encourage you to read that paper if you get a chance. So how do you find relevant research papers and decide which methods to implement? So this is the age-old question. I guess we try a big help to us is partnering with researchers and faculty at universities because they know what's kind of on the cutting edge, right? When you're publishing a paper, you like almost by definition, you have to know what existing methods there are to prove whether your method is better or not, right? So they have that domain knowledge. So working with faculty is very useful. But even if we don't have that collaboration, just take your favorite journal, whatever you find the most interesting. Like there's Journal of Machine Learning Research, there's JASA, there's Annals of Applied Statistics, there's NeurIPS proceedings. There's so many different like conferences and journals and really interesting stuff. So you want to kind of refine that selection of what you're looking for. Like JASA typically tends to have very novel methods that don't exist. They're not typically extensions. So like that would be something like, okay, we're doing fraud detection, for example. We want the latest and greatest method to do that. So we might look at JASA. But if we're doing like marketing, we might want to look to a more applied journal or like a conference proceeding or some sort of machine learning something or another, because those journals are typically more applied in nature. So it really depends on what the business problem is, and then we tailor our research efforts that way. And hopefully, we tend to have a pretty competent team. A lot of them are former researchers themselves. So we had one guy who worked at NASA. He was doing like machine learning research on the Mars rover. So like that was pretty cool. And a lot of the skills that he learned there, you wouldn't think would translate to a bank, but they actually do. And he's a very valuable resource on our team as well. So there's a lot of different avenues in that way. Thanks for the question. Okay. A second case study. Yeah. So so you're asking how industry would typically handle missing values. Um, I hate to be the guy who just keeps giving you it depends answers. Typically you'll want to consider what kind of missingness is it? Is it missing at random, missing completely at random? Is there some sort of structure within the missingness? So there's a lot of exploratory work that goes on beforehand, and using that is what motivates your decision of how to handle it. Um, if and so we have this metadata file, right? So if I go back to this flow diagram on the left side, this purple little document on the left, that metadata has information on like how many missing values do we have? How many unique values are there, right? So if there's 2 unique values, it could be like yes and blank, but we kind of can infer that blank is either no or doesn't apply. There's not really information in that because there's only two unique values. If it was yes, no, and blank, well, we would think that the blank would be impartial, but we don't know. They might not have collected data on that. But if it's just yes and blank, then we know that, okay, they were just asking, like it was a survey or whatever it was. It's like, do you approve this or not, or not? Like, do you approve this? Yes, I do. And so you only collected one side of that. So in that sense, you could convert that to like a binary, like an indicator variable. But other times, if there's like three levels and there's missing value, you have to account for that. You have to find what kind of missingness it is. The one really good thing about machine learning models, like specifically ensemble methods or tree-based models, is they treat the null, like the missing values, as a bucket in and of itself. So there is value in the missing data, right? So like if I have like household type, right? If I have house, apartment, or missing, just because they're missing doesn't mean that they don't have a house. It might mean they live in a van. It might mean that they have multiple houses. It might mean there's different information that is contained within that missing value. So like XGBoost, for example, will treat that as its own separate bucket. So it'll say, okay, what is the performance on those who have a house? What is the performance on those who have an apartment? And what is the performance of those who are labeled as missing? So oftentimes with the machine learning stuff, missing values really aren't a problem because it will automatically account for that. It is a problem in the more traditional statistical frameworks because of the things I was just saying. But so it really kind of depends on like what the business problem is, what the solution we're offering is. And a lot of times, like in generalized linear models, like if we're doing like a logistic family, then there's often ways you can kind of circumvent that as well, depending on like the platform you're using. Like if we have a set of imputation checks, so it goes through and looks to see like, okay, what kind of missing value is it, and then make a decision accordingly. There's also like variable importance scores and things like that where you can look and see like, is there value in this bucket? So you can get pretty crafty with it. Again, this is, I guess, more specific Wells Fargo, but generally other companies have a similar sort of framework. Hope that answers your question. Any other questions?
Well, if not, John, thank you so much for your presentation. Most useful. And please stay in touch with your alma mater.
Definitely. Thank you, guys. Thanks, everyone.